Hey guys, it's Miss Johnson and I'm here to bring you our first part of notes for section 1.2. This is from chapter 1 in our book. I am on page 30 in your book if you want to follow along with where we are. Today we are going to talk about different data displays and also how to describe and compare those displays. We're going to describe and compare distributions of data today. We're going to talk about what necessary components you need to have when you're describing a distribution and how to write those out correctly and accurately and include all of the things that you need to include when you're writing about them. So we are talking about describing distributions. It says how to describe the distribution of a quantitative variable. So now we're moving into quantitative variables, meaning variables that have numerical answers, numerical data, okay? And numerical data is mostly what we work with in this class. So if we're looking at any graph, we want to look for an overall pattern, and we also want to look for clear departures from that pattern. We will describe the overall pattern by describing its shape. We'll also look for its center, and we'll also look for its variability or its spread. Sometimes that's called spread. Another thing that we're going to look for is any outliers that we see in the data, and we also can look for other unusual patterns. So if we see clusters or big gaps or things like that. So anything that falls outside the overall pattern. One thing to note about variability, this is also called spread. So you will hear that word and see that word quite a bit as well. Those AP exam tips that we talked about back in chapter 1.1, it says always be sure to include context when you are describing a distribution. You have to be clear what you're talking about. You're talking about a particular set of data that relates to something. I mentioned in one of our previous notes videos that everything in this class is real life. This is all relating to things that actually happened in the world. So we have to give context when we're talking about these distributions. It says this means we need to use the variable name and not just the number. We also need to use the units of measure. We need to give, inches or centimeters or time or seconds or whatever it may be, or dollars. I mean, there's tons and tons and tons of different labels, and we have to identify what it is that we're talking about. One acronym that you will become familiar with that helps you when you're describing a distribution is SOX. Don't forget your SOX. When you're describing a distribution, you want to describe the shape, the outliers or any unusual patterns, the center, and the spread. You don't necessarily have to go in that order, but that's just an acronym for you to remember. Some people do shape, center, and spread all together and then talk about outliers last or unusual patterns last, and that's fine. It doesn't really matter. Also called variability when we're talking about the spread, but SOX. SOX is a big thing that you're going to remember and that you're going to need to use a lot when you're describing data distributions in this class. So let's just talk about shape. When we are describing shape, we have lots of different shapes that we can identify things as, but these are kind of the main three. You're going to see data that looks roughly symmetric. It's rare for us to use definitive terms like exactly symmetric. We're not going to use things like exactly very often in this class. When you say something is roughly symmetric, this data is real. It's raw. It's not always perfect. It's not going to look super pretty or really neat and clean very often. That's not the real world. So using words like roughly allows you to define something as symmetric, even though you know it's not exactly symmetric. So those of you really, really mathy people in this class may have a hard time with that because usually in math we're dealing with exact things, exact terms, and getting an exact answer. And this class is different. The way we think about statistics is different. So when we see that the right side of the graph is approximately a mirror image of the left side of the graph, excuse me, I'm yawning, then we can say that the data is roughly symmetric. So then skewed. The other thing that you'll see quite a bit in data is skew. It's either skewed to the right or it's skewed to the left. And one thing that I want to point out, so take a look at your data here. If I'm going to draw this out, this data is skewed to the right. My long tail, you're going to hear us talk about the tail a lot. My long tail goes to the right, which means my data is skewed to the right. Skewed to the left, when I look at my data shape here, if I were to draw this out in a curve like that, these are all dot plots, by the way. So if I was going to look at this one, that's what makes it look roughly symmetric. I didn't do that dot plot very well. I could do that better. Let's do that better. Or that drawing. There we go. That's much better. So this one looks roughly symmetric because you've got a center that's roughly in the middle and you've got mirror images roughly on the right and the left side. You can even see that like this one on the left, 1, 2, 3, 4, 5, that's only 5 high. This one is 6 high. So again, it's not perfect, but it's close enough. This skew to the right, tail falls to the right. Skew to the left. Skew to the left is when your tail goes out to the left. Okay, so that's one thing that you need to pay attention to. The direction of the skew is toward the tail. Lots of people want to put it in the direction of the cluster, but it's not. The skew, the tail, those are the things that are going to dramatically change our statistics. The tail up in the far off direction, whether it be to the right or be to the left, that's what's going to change our data and our summary statistics. So that's why we follow the skew. The skew follows the tail, I should say. That's why the skew follows the tail. All right, so here's some other ways that you can think about shape. These are some histograms now. When you're looking at histograms or other displays, you can describe shape in different ways. This first one is symmetric. Unimodal just means that it has one peak in the middle. This one is skewed to the right, which we saw because the tail goes out to the right. This one is bimodal. Bimodal is because it has two peaks. There's two different places that it peaks. This is non-symmetric because this peak is much higher than that peak, so we can't really call that one symmetric. A uniform distribution looks like a rectangle. It's uniform because it's the same all the way across. Skewed to the left, we just talked about. Again, the skew follows the tail. And then this one is symmetric, but bimodal. Okay? You have two peaks here, which is what makes it bimodal, and those peaks are roughly the same height. So since they're roughly the same height, we can call it symmetric. That's what makes these two things different. The peaks are different height here, the peaks are the same height there. All right, so outliers. Outliers are anything that's a departure from the overall pattern of data. You want to look for any extremes, anything that's way down to the left, way up to the right. You want to look for clusters or groups or gaps or things like that. In this case, when I'm looking at my data, I see that a majority of my data is right there. You also have so this is your histogram of the data. Down below, this is the histogram. This is the dot plot of the data. So down below, you can see that in here is where you have a vast majority of your data. But then you've got this one random guy down here and this one random guy way down here. These two things, this one for sure could be called an outlier. Okay, that one's going to be an outlier. This one I would even venture to say is an outlier as well. You've got a pretty big gap between here and the rest of the pattern of the data. So I would say that that could be an outlier as well. So you would describe that as an outlier at approximately -4 and approximately -40, whatever that is, -42 or whatever. And you can determine -44 maybe. You can determine what those values are, or you can just say them approximately. You can say, you know, our data is roughly symmetric with two outliers at -4 and -4 or whatever it is. Center. There's a couple of different ways to mark the center or to talk about the center. One of the ways is the mean and one of the ways is the median. The mean, arithmetic mean, this is the same mean that we've been calculating for years and years and years. Add up all the data and divide by how many there are. It's the most common mean. It's not the only mean There are other means that exist, and we're going to learn some of those this year, but the arithmetic mean is by far the most common. Median, I think we talked about how the median is just in the middle of a highway, right? You've got your highway, here's your other lane going the other direction. This is your median in the middle, with the grass and the trees or the concrete and the signs and whatever. Median is in the middle. So the median is the middle point of an ordered set of data, okay? So those are two ways to describe the center. You may not know what those values are, but you can approximate, or you can give an approximate answer. And then spread. Spread is the interval of values that the data covers. It's a little bit different than range. If I were going to give a range, I'm giving one number. If I say the range of the data is 36, that means that I know that the lowest and the highest point are 36 units apart. If I want to say the spread of the data, I would say the spread of the data goes from 2 to 38. That's an interval. That's listing the variability. That's listing what interval the data falls between. It's more than just listing the range. Range is a version of spread or variability, but range is just a number. Spread is when you give the interval. All right, so we're going to practice doing this with a couple of sets of data because you want to list all four of these things: shape, center, spread, and any outliers, okay? Or in other words, SOCs: shape, outliers, center, spread. So in this first one, it says describe the distribution of goals scored in 20 games played by the 2016 U.S. women's soccer team. So here's our dot plot. We've got a dot plot here. You're going to see dot plots a lot in this class. So we've got a dot plot. We see that there were 6 games that they scored 1 goal, 5 games they scored 2 goals, 3 games they scored 3 goals, 1 game they scored 4 goals, 3 games they scored 5 goals, and then way up at the top, 1 game they scored 9 goals, and 1 game they scored 10 goals. Okay, so take a look at your data here. Here's what they say about these things. For shape, it says the distribution of goals scored is skewed to the right. If I were going to draw this in terms of a curve, which we'll be drawing a lot of curves in this class as well, my tail is way up here to the right. Okay, so that's why it's skewed to the right, with a single peak at 1 goal, and there is a gap between 5 and 9 goals. Okay, those are all things that talk about the shape. Outliers. The games when the team scored 9 and 10 goals appear to be outliers. Center. So that was outliers. Center. The median goal scored is 2. And you can actually determine this. If I was going to determine the median here, I would literally count the middle. So I know I'm looking at 20 games total. That means that the median is going to be between the 10th and 11th, game or points, data point. So if I count here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And if I averaged those out, they're both at 2. So 2 plus 2 divided by 2 would be 4 divided by 2, which gives me 2. So my median there is 2. I actually found this. I know this to be true. The next thing I would find is the variability. So the number of goals scored varies from 1 to 10 goals. So you can see how they list the interval there. It's not just about listing the range. I would say that the range of the goals scored here is 9, but that's not what they're looking for. They're looking for spread or variability. So you're looking for an interval. All right. One other thing to make sure that we did we include context? And the answer is yes. Every single statement referenced goals. The distribution of goals scored with a single peak at 1 goal. There's a gap between 5 and 9 goals. The games where the team scored 9 and 10 goals appear to be the outlier. The median is 2 goals scored. The number of goals varies from 1 to 10 goals. So all of that is necessary. If you don't put context in your sentences, you will automatically lose credit if this were the AP exam. You have to list that context. All right, so now let's talk about comparing two different distributions. When it says we used census at schools, random data selector to choose 50, there's your N, students from each country. Here are the dot plots of the household sizes reported by the survey respondents. Compare the distributions of the household size for these two countries. So we're looking at the United Kingdom and we're looking at South Africa, and this is the household size of 50 randomly selected students. Okay. You see two dot plots. One thing to take note of, when you look at those dot plots, the x-axis is the same. Okay, so do you see that my x-axis lines up? My 0 lines up with my 0, my 5 lines up with my 5, my 10 lines up with my 10, my 15 lines up with my 15, and so on. The x-axis is also labeled for both household size and household size. Each graph is labeled with the country name, and it also says country in front of both of them. So all of those things are important when you're looking at two different things, especially that lining up the x-axes. You can't compare two data sets if you don't put them on the same type of graph. It doesn't work. So look at the AP exam tip down here. It says when comparing distributions of quantitative data, it's not enough just to list values for the center and variability for each distribution. You must explicitly compare these values using words like greater than or less than or about the same as. So you can list them both, but you also need to actually use comparative language to describe them. Okay, so in this case, it says we used census at schools. Oh, this is the same thing. This is their description. So for shape, the distribution of household size for the United Kingdom sample is roughly symmetric with a single peak at 4 people. There's the context. The distribution of household size for South Africa sample is skewed to the right with a single peak at 4 people. Again, there's the context. And they also explicitly say there's a clear gap between 15 and 26. So you've got a shape for both countries. I've got a shape for the United Kingdom and I've got a shape for South Africa. I list the context, meaning people. I talk about the gaps. Okay, so there's that for shape for both. Now let's look at the outliers. For outliers, it says there don't appear to be any outliers in the United Kingdom distribution. Okay, check. So we talked about United Kingdom. And then the South African distribution seems to have 2 outliers. The households with 15 and 26 people, context, check. So what they're looking at is this and this right here as outliers. Okay, and over here, no outliers. Okay, then center. Household sizes for South African people tend to be larger. There's your comparative language than for the UK students. They also went as far as actually determining the median for both. Now I want you to cross off something here because there is actually a slight mistake. These 5s are a little bit rogue. It's not supposed to be a median of 56 people and 54 people. It's supposed to be a median of 6 people and a median of 4 people. But you can actually calculate the median here. You could count the 25th data point. You're looking at groups of 50 for each. Each group is a group of 50 data points. That means the 25th data point is the median. So if I went through and counted my dot plot, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. For South Africa, there's my median of 6. And same thing, I could count my data points and I'd be up here somewhere for a median of 4. So median can actually be calculated when you're looking at a dot plot. Median is possible in a dot plot. Okay, so again, they used comparative language. South African homes tend to be larger. Their median is 6 people. The United K students have a median of 4 people. Okay, the last thing, spread and variability. The household sizes for the South African students vary more from 3 to 36 people. 3 to 26 people than the United K students who vary from 2 to 6 people. So South African homes have more variability, right there up to there. Whereas the United Kingdom homes have variability from only there to there, from 2 to 6. So again, comparative language, vary more, and listing those intervals with context of using the word people. All of those things are important. You are going to write a lot in this class. You are going to spend a lot of time formulating clear and constructive sentences that have complete information in them. If you were not expecting that, I'm warning you now. You're going to write a lot in this class. All right, that's to the end of our notes for today. Thanks for listening. We will pick up with the second half of section 1.2 next time.